Hello everyone, the humble math tutor here. Today we're going to evaluate a definite integral using Riemann sums. This video emphasizes the mechanics of using a four-step process to quickly get to the answer. This is the question we will work on today. Evaluate this integral using Riemann sums. As I said, there are four steps. The first step is to evaluate delta x. And that is always b minus a over n, where a and b are the bounds of integration. Here, 2 and 5. So this would be 5 minus 2 over n, which is 3 over n. One step down, 3 to go. The second step is to compute xi. Xi is always equal to a plus delta x times I, where delta x is taken from step 1. This would be 2, remember, a is the lower bound of integration, 2, plus delta x times I. And that works out to be 2 plus 3i over n. 2 steps down, 2 to go. The third step is to create an expression for f at xi. Now remember, f at x is 2x plus 3. So it stands to reason that f at xi would be 2xi plus 3. But xi was computed in step 2. So that would give us 2 times 2 plus 3i over n plus 3. Multiply through the binomial by the 2 in front, and you would get 4 plus 6i over n plus 3, which simplifies to 7 plus 6i over n. On to step 4. Step 4 is to use this. The integral from 2 to 5 of the function is equal to the limit as n approaches infinity. You must memorize this part. I equals 1 to n of delta x f at xi. And you simply work through the right side as follows. This will be the limit as n approaches infinity of the sum from I equals 1 to n. Delta x from step 1 was 3 over n, and f at xi from step 3 was 7 plus 6i over n. Multiply through the brackets. You always do that at this stage. Don't leave it as a factored form. And this will be limit as n approaches infinity of the sum from I equals 1 to n of 21 over n plus 18i over n squared. Next, what we want to do is distribute the sum symbol through the brackets. So it'll be the sum of this guy plus the sum of this guy. Leave the lim out front. You don't need to migrate him through into the brackets. Just the sum symbol. So that would give us this. I'll write that instruction down. It's pretty important. So distribute the sum symbol through the brackets, but not the lim symbol. So that would give us this, the limit as n approaches infinity of the sum of 21 over n plus the sum of 18i over n squared. Remember, those do run from 1 to n. Next thing you do is this. You move any numbers and any n's to the left side of each sum symbol. That's the most difficult instruction to find. That's the most difficult thing to think of at this point. It's the number one place where students go wrong in this type of question. So that means 21 over n is going to move here, and 18 over n squared will move here. Not the I, just any numbers and any n's move to the front. So that's going to give us the limit as n approaches infinity of 21 over n times the sum of. Now remember, there's an invisible 1 here. I'm going to leave it in position here because we know we're going to be accessing our Riemann sum formulas in a minute, right? And look at the top one. it's the sum of 1 n times. It's equal to n. We're going to need that guy. So for that reason, I'm going to leave a 1 here, an invisible, currently invisible, but I'm going to leave him there in position. And that goes from I equals 1 to n plus, and this is 18 over n squared times the sum from 1 to n of simply I. That was a tough instruction to follow. That's a difficult one to think of when you're in the middle of all the calculations. But wait a sec, these guys are found in the list, aren't they? Like the second guy on the list, there he is, the sum of I. That's what appears here. And the top one, the sum of 1. It's n. So these guys can be substituted in here now, can't they? So this guy here, he's just is equal to n using the Riemann sum formulas, right? And this guy here, he's just simply n times n plus 1 over 2. So now the rest of it is fairly straightforward. That gives us this equals the limit as n approaches infinity of 21 over n times n plus 18 over n squared times n plus 1 over 2. Simplify. Simplify. The n's cancel here, and that will give us equals limit as n approaches infinity of simply 21 plus, and here 18 over 2 is 9, and one of these two n's will cancel with this n, giving us the following, n plus 1 over n. And I need to compute the limit as n approaches infinity of this expression. Well, the limit of a constant is just a constant, and that's going to be 21. And this 9 is going to stay as a 9. This guy's critical, though. Well, there's one way to compute it, which is fast, and that is just do the lead coefficient method. And so you could actually say, well, that's 1 here, and that's an invisible 1 there. And as n approaches infinity, you could take the limit as 1. If your professor requires more work to show you how that limit works out, then what you could do is use this strategy. Divide top and bottom of this fraction by n to the highest exponent you see. So I'll divide the top by n, and I'll divide the bottom by n. Look what we get on the next line. It's a very professional way to thoroughly show you understand the limit. So that would give us this on the next line, wouldn't it? I'd have this now. Here we go. Watch this. So this would be equal to the limit as n approaches infinity of 21 plus 9 times. Now when I divide n into this, I get 1. When I divide n into this, I get 1 over n. And when I divide n into n, I get 1. So what happens as n approaches infinity? Well, it's very clear now. This guy here approaches 0. So now I have my limit. I've executed this answer here. I don't write lim anymore because I've actually executed the limit. See the green ink? And that would be 21 plus 9 times, and this guy would be 1 plus 0 over 1. And that would be 21 plus 9, which is 30 square units under the graph from 2 to 5. There we go. If you enjoyed this video, please like, subscribe, and share. Thank you very much.